Hello students, today we will continue with the topic regression with a single regressor, and in particular we will talk about hypothesis tests and confidence intervals. So to give a quick recap of the ideas that we have so far talked about, basically we have defined a population regression function . We have defined a population regression function where we have said y is expressed as a linear function. Y is the dependent variable, is expressed as a linear function of the independent variable x, and there is an error associated within this population regression function. Then we have collected a data and we have estimated a predicted regression line which is given as y hat is equal to beta 0 hat plus beta 1 hat x plus ui hat. In this particular case you could also have the indices I for here, and here yi hat is equal to beta 0 hat plus beta 1 hat xi plus ui hat. Then we had said this estimation is done by the means of ordinary least square estimation, where basically we tried to minimize the sum of squared errors, or we tried to fit a line where the line would pass through the middle of a cloud of points, and we tried to find the slope and the intercept of this particular line, which would give the best representative of the typical relationship between y and x. And this is the beta 0 hat, which is the beta 1 hat that we try to estimate, and if you were to look at this, then this is the beta 0 hat, which is the intercept also that we try to estimate. Then we had looked at measures of fit, and so we had looked at R square. Measures of fit, we had looked at two different things, which is R square, which was the amount of variance explained by the regression by the total variance, variance explained by the total variance in y. And then we had also looked at the idea of standard error of regression. But most importantly, we had introduced the three least square assumptions. The three least square assumptions, the first one of which was that expected value of u given x is equal to 0. The second one of which was that the x's and y's were IID, and the third one of which was that variance of y as well as variance of x was both bounded. So it did not have, there were no large outliers. Under these least square assumptions, then we introduced the idea of the sampling distribution for the estimated parameters beta 0 hat and beta 1 hat. Now when we talk of sampling distribution, basically we introduce the idea that for this particular sample, we have estimated a particular value of beta 0 hat and beta 1 hat, but had we taken a different sample, then we might have estimated or we might have arrived at a different estimated value of beta 0 hat and beta 1 hat, and hence the values of beta 0 hat and beta 1 hat themselves follow a certain distribution which has the mean of that sampling distribution, and which has also a variance. These are the ideas that we have introduced so far. Given that we have introduced these ideas, now we describe how to conduct hypothesis tests regarding our estimated parameters beta 0 hat and beta 1 hat. And in order to do that, this is the outline of today's the lectures that we will go through. First, we will introduce the idea of the standard error of beta 1 hat, which is related to the variance of beta 1 hat from the sampling distribution. So, standard error of beta 1 hat, we will say that there is an error associated with beta 1 hat. Taking this standard error into account, then we will state some, if we want to state some null hypothesis regarding beta 0 or beta 1 hat, using this value of standard error, we can then test those hypotheses. Then we will use the same standard error to create confidence intervals for the beta 0 hat and beta 1 hat at certain levels of confidence. Next, we will introduce the idea of what regression means when we have a binary independent variable. So, when it is not a continuous independent variable, but a variable which takes only two values, then it's a binary independent variable. Then how do we do regression? And finally, we will introduce the idea of heteroskedasticity and homoskedasticity. This is the outline of the lectures that we will follow now. Okay. So, to give a big picture view, we want to learn about the slope of the population regression line. Remember that we are actually interested in the population regression line. We do not have data for the population, and hence we get data from a particular sample, and because we are getting a data from a particular sample and we could as well have included other entities in the sample or got a different sample, so there is a sampling uncertainty associated with the parameters that we estimate. So, first we state the population object of interest, then we provide an estimator, we derive the sampling distribution of the estimator, which will require certain assumptions, which in our case are the least square assumptions. In large samples, this sampling distribution will be normal by the central limit theorem. The square root of the estimated variance of the sampling distribution is called the standard error of the estimator, and we will use the standard error to construct t-statistics and conduct hypothesis tests about the parameters that we estimate, and we will also arrive at confidence intervals. So, this is our outline of what we are basically trying to do. Please notice the analogy with if you want to understand something about the mean of the population, this is exactly the same thing that you do. You create, you take a particular sample, you calculate the mean, and then you try to test hypothesis about the mean, which we have discussed before. So, in our particular case, we are not interested in the mean, but we are interested in the slope or the beta 1 hat. That is, what is the change in what is beta 1 hat? I am sorry, let us see. So, what is beta 1 hat? Beta 1 hat is given by the change in y, delta y by delta x in this particular when y is given as a linear function of x. Then what is the change in y for a unit change in x? So, we are really interested in beta 1 hat. We arrive at the OLS estimator beta 1 hat, and we have talked about the sampling distribution of beta 1 hat under the following least square assumptions, which we have already stated before. So, under the least square assumptions, as we have stated before, we have said that the beta 1 hat, if you have a large sample, the beta 1 hat, the mean of beta 1 hat tends towards the true population mean. This is a law of large numbers, and also beta 1 hat has is distributed in terms of a normal distribution, and this is the variance of beta 1 hat that we had suggested that this is how this variance is derived, we had not looked at, but basically the variance of beta 1 hat is given by this formula, where sigma square v, where the numerator is given by vi equals to xi minus mu x multiplied by ui, and the denominator is given as the variance of x, the square of the variance of x multiplied by n. So this is the variance of beta 1 hat that it will tend towards in large samples. So this is the distribution of, this is the sampling distribution of beta 1 hat. So given that that is the sampling distribution of beta 1 hat, how do we go about doing hypothesis tests and arriving at the standard error? So the objective is to test a hypothesis. So the hypothesis could be that beta 1 is 0, that is there is basically no relationship between y and x. Y is given as a function of x, where y is equal to beta 0 plus beta 1 into x. But if beta 1 is 0, that means y is not a function of x. So in a more general manner, if we will not start with beta 1 is equal to 0 is a particular null hypothesis, but suppose we say that beta 1 is equal to some hypothesized value under the null. This is a two-sided alternative, that beta 1 is equal to that hypothesized value versus beta 1 is not equal to the hypothesized value. That hypothesized value may be 0 or that hypothesized value may be something else. We could also have a one-sided alternative where we say that the null hypothesis is, the alternate hypothesis is beta 1 is less than some hypothesized value, and the alternate is beta 1 is greater than equal to the hypothesized value. These are the kinds of hypotheses that we might state. So what do? We construct a t-statistic or we construct a z-statistic where the numerator is the estimated value minus the hypothesized value divided by the standard error of the estimator. Okay, this is generally what we do, right? When we are doing hypothesis testing, we say we create the z value as x bar minus mu x divided by standard deviation of x. Standard error. Remember that this is a standard error of x bar. Okay. This is the z statistic that we have usually, and standard error is equal to sigma x divided by root of n. Okay, or sx divided by root of n. So this is the standard error of x bar. This is when we are testing for the mean. In this particular case, we are not testing for the mean, rather we are testing something about the beta 1 hat. So we need to get the standard error of beta 1 hat, and we need to see what is the estimated value of the beta 1 hat minus the hypothesized value, whatever we are saying is the hypothesized value. So this one will be, so the t-statistic in the particular case of the mean, as we said, t-statistic is given as y bar minus mu y divided by sy by root of n. In the case of beta 1, we say beta 1 t-statistic is the beta 1 hat, which is the estimated value minus the hypothesized value divided by the standard error of beta 1 hat. And what is the standard error of beta 1 hat? Standard error of beta 1 hat is the square root of an estimator of the variance of the sampling distribution of beta 1 hat. So just like the square root of the variance in this particular case is the standard deviation, here also we are looking at the square root of the variance of the sampling distribution of beta 1 hat. So the formula for standard error of beta 1 hat is given like this. We have said that the variance of beta 1 hat when in large samples, the variance of beta 1 hat is given by this complicated looking formula, where it is variance of xi minus mu x multiplied by ui divided by n variance of x whole square. So this is given by this whole thing in the numerator. We sort of substitute it by saying it is sigma square v, where vi is defined as xi minus mu x multiplied by ui. Okay, so this is the quantity and the variance of that is in the numerator, and in the denominator we have n times square of the variance of x. So the estimator of the variance of beta 1 x replaces the unknown value population values of sigma square v and sigma square x over here by estimators constructed from the data. So from the data you will have actual values of xi, x bar and ui. Ui is, you get the values of ui once you have fit a particular regression line, then ui is equal to yi minus yi hat. For each value of I, yi minus yi hat will give you the values of ui. So this is the variance of beta 1, 1 by n. This is the variance of beta 1, and you can calculate this. So given that this is the variance, the standard error is the square root of this variance, or this is the standard error of beta 1 hat. So the numerator estimates the variance of v, where v is this particular quantity xi minus x bar multiplied by ui hat, and ui hat, as we have said, ui hat is given as yi minus yi hat, which is equal to yi minus beta 0 hat plus beta 1 hat xi. So for each particular ith observation, you have the associated xi's and yi's, and you have the associated beta 0 hats, and you have already estimated beta 0 hat and beta 1 hat by OLS. So you just plug in these values over here and you get the values of ui hat. This quantity multiplied by ui hat, the variance of this total quantity is what is there in the numerator. In the numerator you divide it by n minus 2. This is again a degrees of freedom correction, because in order to arrive at this numerator you have estimated two parameters, and the number of free parameters that are left are the total number n minus the parameters that you have estimated, which is 2. Okay, so two coefficients have been estimated, beta 0 and beta 1. Now in reality, SE standard error of beta 1 hat is computed by the regression software. So whichever software that you use, R, SPSS, this will calculate this sort of somewhat complicated looking formula for you, but you have to understand what the standard error. So basically the idea is that the regression software will give you the standard error associated with each beta 0 hat and beta 1 hat coefficient that you estimate from your data, and you have to understand what this standard error is that your software is giving you. So your regression software has memorized this formula, so you don't need to memorize, but you do have to understand what it stands for. So to test beta 1 equals to beta 1 0, that is some hypothesized value, versus the null alternate hypothesis that beta 1 is not equal to beta 1 0. So your software will spit out some value of standard error of beta 1 hat. So your t-statistic, which also incidentally your software will give you, the t-statistic will be the estimated beta 1 hat minus whatever is the hypothesized value, which, if it is not stated otherwise, usually the null hypothesis is that beta 1 hat, null hypothesis is beta 1 is equal to 0. This is the null hypothesis. So I'm sorry, this it will not be a hat over here. The estimated value minus the null hypothesis and divided by the standard error of beta 1 hat, that will be the t-statistic. And given that you have the t-statistic and given that the sampling distribution is a normal distribution, follows this t-statistics follows a standard normal distribution. So you can check using a standard normal table, and if this t-statistic is more than 1.96, as you know that 1.96 is the critical value for confidence tests at a 95% confidence level. So if it is greater than 1.96, then you can reject the null hypothesis at a 95% confidence level. I'm sorry, here it says 5%, but it is actually 95% confidence level. Okay, so if you have a large n, and if you typically n equals to 50 is large enough for the approximation to be excellent. So if you have more than 50 data points from which you have found your regression coefficients, then you can use this t-statistic and you can do hypothesis testing. So let us look at the particular example that we were talking about, which is the test score and STR. So as we know, the estimated equation is test score hat is equal to this is beta 0 hat 698.9. I'm sorry. Okay, and this is beta 1 hat, that is minus 2.28. This is beta 0 hat and this is beta 1 hat. So you substitute that value. So test score hat is given as 698.9 minus 2.28 into STR. So this is your predicted test score. The regression software reports the standard errors as this. So the standard error in this particular case, given from that complicated looking formula, the software has told you that the standard error for beta 0 hat is 10.4 and the standard error for beta 1 hat is 0.52. So the t-statistic when you are testing the null hypothesis that the beta 1 is equal to 0, that is there is no correlation between test score and STR, then you take your estimated beta 1 hat, which is minus 2.28 minus 0 divided by the standard error of beta 1 hat, which is 0.52, and you get a t-statistic of minus 4.38. Now, because this minus 4.38 is greater than 1.96, then you can definitely reject the null hypothesis at the 95% confidence level. But since it is even greater than 2.58, you can also reject the null hypothesis at the 99% confidence level. So basically, there is no doubt at all that there is definitely a negative correlation, and when you reject it at a 99% confidence level, you are rejecting the null hypothesis that beta 1 hat is equal to 0. So you are saying it is not equal to 0, and there is in fact a correlation, a negative correlation between test score and STR. Now, what is the p-value approach? You could either use the rejection area approach, where you a priori determine the alpha level, that is the 5%, 95% confidence level, 99% confidence level, alpha of 5% or 1%. You could a priori determine that. Or you could say that given that you have arrived at a value of 4.38, minus 4.38 in this particular case, what is the probability of having arrived at an even more extreme value if your null hypothesis were true? If your null hypothesis were true, how likely is it that you would have got a value which is even more extreme than minus 4.38? So that is the area of the curve which is beyond minus 4.38 on this side and beyond 4.38 on this side, because it is a two-sided hypothesis, and the p-value, the probability, is very, very, very small, that is 10 to the power of minus 5. So what that is indicating to you is that this minus 4.38 is a very extreme value, and which basically means that your mean, the the beta 1 hat is equal to 0, you will reject the null hypothesis that the beta 1 hat is actually equal to 0. It is probably not equal to 0, it is somewhere closer to minus 4.38, and the probability is very small that you would have got such a high value or such a large value of the t-statistic if in fact your null hypothesis were true. So this is the p-value approach, by looking at the actual probability beyond that value that you have got. Now we come to, so here we just reject the null hypothesis, where we have previously we have just stated a null hypothesis, that is beta 1 is equal to 0. But when you reject the null hypothesis, all that you are saying is that beta 1 is not equal to 0. Beta 1 hat is not equal to 0. So can you do better than that? You know, yes, okay, it is not equal to 0, but what is it actually? Is it like, you know, whatever, minus 2.28, is minus 2.28 what it is, or is there a range of values between which it may vary if you had taken a different sample? So that is what you get by looking at the confidence interval around minus 2.28. So that 95% confidence is the set of points that cannot be rejected at the 5% significant level. So it is a set valued function of the data, an interval that is a function of the data that contains the true parameter value 95% of the time in repeated samples. Had you taken another sample and then another sample, what is the range of values within which your beta 1 hat would lie? Okay, so that you basically take as this range of values, or this confidence interval is given by the estimated beta 1 hat plus minus 1.96 multiplied by the standard error of beta 1 hat. So the estimated beta 1 hat also you know, and the standard error of the beta 1 hat also you know, which your software has given you. Given that you know both these values, so you can now say with 95% confidence that what your actual values, what is the real relationship, or what is the range of values which will give you the real relationship between y and x. And this is often a better way of understanding the relationship between y and x. So in this particular case, the test score hat is 698.9 minus 2.28 into STR. Minus 2.28 is your beta 1 hat plus minus 1.96 multiplied by 0.52. If you remember, the standard error of beta 1 hat as calculated by the software was 0.52. So you do this, minus 2.28 minus 1.96 into 0.52 is minus 3.30. Minus 2.28 plus 1.96 into 0.52 is minus 1.26. So you will notice that your 95% confidence level goes from minus 3.3 to minus 1.26. Both of these values are negative. That means with 95% confidence, you can say that there is in fact a negative correlation between y and x. So the 95% confidence interval does not include 0, and because it does not include 0, the hypothesis beta 1 is equal to 0 is rejected at the 5% level. So both are saying the same thing. The 95% confidence level both fall under 0, and you have also rejected the null hypothesis that the beta 1 equals to 0 using the t-statistic. Both of these are equivalent statements. So how can you report regressions using all of these things that you have looked at? So you can report regressions in this way, where you can say test score hat, this test score hat is equal to 698.9 minus 2.28 into STR. This is beta 0 hat minus beta 1 hat into STR. Under beta 0 hat, within brackets, you put the standard error of beta 0 hat, and under beta 1 hat, within brackets, you put the standard error of beta 1 hat. Okay, so this is the standard error of beta 0 hat, and this is the standard error of beta 1 hat. So once you have start building models, this is how you should report your model as a single linear function. And R square is 0.05 and standard error of the regression is 18.6. So by giving 1, 2, 3, 4, 5, 6 numbers that you are reporting, you are basically telling your reader a lot of ideas of what your regression is like and how well your regression line fits the data, and whether there is in fact a statistically significant correlation between your test score and STR. Okay. So as we notice, this expression gives a lot of information. The estimated regression line is test score equals to 698.9 minus 2.28 into STR. The standard error of beta 0 hat is 10.4. The standard error of beta 1 hat is 0.52. Using this data, you can calculate t-statistics. T-statistic is equal to beta 0 hat minus the hypothesized value divided by the standard error of beta 0 hat, and t-statistic for this is the t-statistic for beta 0 hat, and the t-statistic for beta 1 hat is equal to beta 1 hat minus the hypothesized value divided by the standard error of beta 1 hat. Okay, and then we also know that the regression R square is 0.05, that you have your X explains only 5% of the variation in Y. That also is given in this formulation, and we also know what the standard error of the regression is, or what is the standard deviation of the errors in the regression. So this in a very concise manner, all of this information is given in this particular line. So let us look at how the output looks at. So we have seen this output before. As we said, we have found the coefficients. Here the coefficients have been given. We have looked at the standard errors. The regression output gives you the associated standard errors for the constant, which is the standard error for beta 0 hat, and the standard error for beta 1 hat. It also gives you the associated t-statistics. It also gives you the p-value associated with each of these t-statistics, and finally it gives you the 95% confidence interval for both beta 1 hat and beta 0 hat. So this is what your typical statistical output might look like, and this is how you interpret that statistical output. So to summarize, summary of statistical inference about beta 0 and beta 1, we estimate using OLS estimators beta 0 hat and beta 1 hat. Beta 0 hat and beta 1 hat have approximately normal sampling distributions in large samples. The testing, when we test, do a hypothesis test, we test the hypothesis, null hypothesis, that beta 1 is equal to some hypothesized value beta 1 0, which often is taken as 0, versus the alternate hypothesis that beta 1 is not equal to that hypothesized value. And we calculate a t-statistic, which is beta 1 hat minus beta 1 0 divided by the standard error of beta 1 hat. Then we get the p-value, given that this t-statistic will be distributed according to the standard normal distribution, given that the fact that there is under large n by CLT, this t-statistic will be distributed by according to the standard normal distribution. So the p-value will be the area under the standard normal outside the actual t statistic that you have calculated. Okay, and then we can get at the confidence intervals for the beta 1 hat parameters, and this is the set of beta 1 that is not rejected at the 5% level. So the 95% confidence intervals contains the true beta 1 in 95% of all samples. So this is where we will end today's lecture, and we will continue in the next lecture about the binary dependent variables and the idea of heteroskedasticity and homoskedasticity.